Dear students, today is the third class of renal physiology, and this class is for glomerular physiology. That means physiology of glomerular filtration or glomerular activity. And what is glomerulus? That I have been discussed and detailed in last two classes. So I will now share the screen and I do my presentation. So this is the physiology of glomerulus. That is the title of my presentation. And this is one of the very important and topic of renal physiology, which all of you must understand. Now, physiology of glomerulus, I will take up one by one. So this is a typical nephron. Typical nephron I have shown you earlier also, where we can see the glomerulus proximal tubule. Then this is the loop of Henle. This is descending limb of loop of Henle. This is ascending limb of loop of Henle. Distal tubule, connecting tubule, collecting tubule, and this is the corticomedullary orientation of the nephron. Now, in that, so from today onward, we shall take up each portion of the nephron at a time and try to understand the physiology of that part. And today's assignment is glomerulus. So what is glomerulus? So this is glomerulus. This is glomerulus. The whole thing also sometimes called Malpighian corpuscle. Now, truly speaking, Malpighian corpuscle, what is shown here, Malpighian corpuscle, has got two distinct parts. One is glomerulus, another is Bowman's capsule. Glomerulus and Bowman's capsule. And accordingly, it is a junction of endothelium and epithelium component. So this is a junction of epithelium and endothelium. That means glomerular capillary endothelium and tubular epithelium. I repeat, glomerular capillary endothelium and tubular epithelium or Bowman's capsule epithelium. They are coming in very close contact and it forms the Malpighian corpuscle. Now, if we just see the picture of the nephron, which I have described plenty of times during last two classes. So this is the picture of a nephron, schematic picture of a nephron. So this is Malpighian corpuscle. Red is the glomerular capillary plexus. This is Bowman's capsule. This is descending limb. Here is the proximal tubule, then descending limb of loop of Henle, ascending limb of loop of Henle, connecting tubule and collecting tubule, which is ultimately urine formed. So here is the filtration is taking place throughout the tubule. The filtrate processing, that means transport, is taking place. Either addition, that means secretion, or removal, that means reabsorption, is taking place, and finally processed filtrate, that is urine, is formed. Now, if we now, if you try to understand one by one, so this is the part which is the point of discussion today. Now, here I am showing the glomerulus, plenty of glomerulus. This is taken from an animal kidney, mammalian kidney. This is a resin cast with scanning electron microscope. You can see clearly the glomerular tufts connected with the afferent and efferent arteriole, and from where this tubule is originating. Now we are mainly interested with this portion, the glomerulus. If I magnify it like this, if I magnify it, so we can gradually magnify and can see this is the glomerular capillary duct, and it is connected with the afferent and efferent arteriole, from where ultimately the collecting and collecting tubular emerging to finally reaching the throughout the medulla, it is coming down, something like that. This is a picture of a typical glomerular capillary, and this is the afferent arteriole and this is the efferent arteriole. So afferent arteriole forming capillary plexus followed by efferent arteriole, and that is the speciality of the glomerular capillary. It is originating from an arteriole and end up in an arteriole, in contradistinction to any other kind of capillary. So this is a simple microscope picture, ordinary microscope picture of a glomerulus, where we can see the glomerular capillary plexus. These are the glomerular capillary plexus, and this is the Bowman's capsule. This is the parietal layer of Bowman's capsule. This is the visceral layer of Bowman's capsule. This is the parietal layer of Bowman's capsule, from which the tubular epithelium is originating. Again, it is a scanning electron microscope of glomerulus. This is the glomerular capillary plexus, and here are the two afferent and efferent arteriole, which is moving like that. So, if we magnify to visualize the glomerular capillary plexus, you can see clearly that these glomerular capillary plexus has got certain complex structures. Actually, what is happening? Capillary as such is a very complex structure on which Bowman capsule epithelium is invested on it. The surface of the Bowman's capsule, or what I should say, the visceral layer of the Bowman's capsule, is intimately and intricately invested on the capillary, and the end part is forming the capsule, which is continuing as the renal tubule. So this is the zone where the capillary endothelium and Bowman's capsule epithelium, they are coming in very close contact, and in that close contact, the epithelial side is forming certain food processes, and by that it is resting on the basement membrane. Truly speaking, glomerular filtration barrier or glomerular barrier across which this filtration is taking place is a three-layered structure, and only continuous layer is the basement membrane, and in two sides, one side is the capillary endothelium, in other side is the Bowman's capsule epithelium. I will show you the clear-cut picture. Now this epithelial side, Bowman's capsule epithelial side, they are associated with the basement membrane in the form of a foot process. I will show you very clear pictures. So this is scanning electron microscope. I am continuously magnifying it, and you can see the foot processes. That means, it is also known as podocytes. Podocytes means cell which are having feet. So with this feet, it is resting on the basement membrane. So this is further magnification, and we can clearly see the foot processes in the scanning electron microscope. So if we see in the schematic diagram, we can see like that. This is the basement membrane or basal lamina. In one side there is capillary endothelium. In other side there is Bowman's capsule epithelium. And this Bowman's capsule epithelium is resting on the basal lamina by certain food processes. So these food processes resting associated with the basal lamina with certain food processes, and this endothelium has got pores or fenestration, which you can very clearly see. There are pores and fenestration on this glomerular capillary endothelium. And these three, in one side endothelium, in other side epithelium, in between the continuous layer is basal lamina or basement membrane. All these three combination is forming the filtration barrier or filtration sheet, right? Now, if we further magnify this portion, let us see. So you can very clearly see the only one continuous layer is the basement membrane. In this side, there is capillary endothelium with fenestration or pores. In other side, Bowman's capsule epithelium with food processes. And this picture is typically the picture of the filtration barrier across which the filtration is taking place. And in the endothelium side, we can see these fenestrations. These fenestrations, you can see, these are the fenestrations, these are the fenestrations. Now, these fenestrations and these slits between the two food processes. So there is a slit between the two food processes, and there are hole, pore, or fenestration through which the different solute molecules or various molecules can pass through. And these slits, gap between the slits or pores and fenestration, they will determine the permeability property or permeability characteristics of this filtration barrier. They will determine the permeability characteristics of this filtration barrier. So this is another transmission electron microscope of the this filtration barrier. We can clearly see these are the food processes. And these are the capillary endothelium fenestrations. We can clearly see. Now these slits between the food processes are having a diameter of 500 to 1000 angstrom. So this is the transmission electron microscope, TEMS, transmission electron microscope picture of filtration barrier. In one side there is epithelial food processes, in other side the fenestrated capillary endothelium, and in between the basal lamina or basement membrane, which is the only continuous layer. Now, if we now see the filtration barrier, other side. So filtration barrier, we can very clearly see the filtration pores. So this is a scanning electron microscope of the inner side of the filtration barrier. So you can see the pores very clearly. If we magnify it, suppose we magnify it, you can very clearly see the pores. So these are the pores, you can clearly see, and the pore diameter is around 500 to 1000 angstrom. 500 to 1000 angstrom, that is the pore diameter. Now, whole of these pictures we can summarize on this schematic diagram. Whole of these pictures. So we can see this is the capillary endothelium. So this is a cross section of the capillary. This is capillary endothelium. Any capillary is a single layer structure based on the basement membrane. So this is a single layer capillary and having pores or fenestrations. And these are the food processes, and this is the slits between the food processes, right? And this is the slit between the food processes, and as a whole, this is and this is creating the filtration barrier. So, filtration barrier, as the name suggests, it is the barrier for filtration. It is a barrier across which the filtration is taking place. What is filtration? Filtration means, physiologically, filtration is defined as that phenomena where there is a passage of molecules along pressure gradient. It is the passage of molecule along pressure gradient. As we know that diffusion means passage of molecule along concentration gradient, filtration means passage of molecule along pressure gradient. Now, to filtration to occur or the extent of filtration, there are three determining factors. One is size, and there is charge, and there is shape of the molecule. So we are seeing. So the size of the molecule or size principle, charge of the molecule or charge principle, and shape of the molecule, that is shape principle. Size means if the molecule is having a molecular weight of 5,000 or less, then it is easily filtered across the glomerular filtration barrier. So all the molecules, all the substances present in the plasma other than proteins, all the substances present in the plasma, most of the substances present in the plasma other than proteins can easily pass through the glomerular filtration. All the electrolytes, organic compounds like glucose, urea, etc., glucose, urea, uric acid, etc., all the electrolytes like sodium, potassium, bicarbonate, calcium, chloride, etc., all can easily pass through the filtration barrier. As far as charge is concerned, this filtration barrier is having a negatively charged sialoproteins. So if the molecule is positively charged or positively charged solute particles, they can pass across the filtration barrier more easily. And negatively charged particles or negatively charged substances, they are rather repelled, like proteins, albumins, etc. They are facing lot of difficulty, or they cannot pass through this glomerular filtration barrier, whereas charged particles or positively charged particles or cationic substances, they can pass more easily. And third is the shape principle. If the substance is more compact in shape, it can pass better. Or if the substance is rather asymmetric in shape, cylindrical in shape, not that compact, it faces a lot of difficulty in passing through the basement membrane. If I give example, as for example, the albumin and hemoglobin, both this molecule having a molecular weight of around 68,000, approximately 68,000, both albumin and hemoglobin. But hemoglobin is passing 3 times more than albumin. Why? Because hemoglobin is a more compact substance than albumin. Hemoglobin's compactness, shape of hemoglobin is more compact than albumin. Both the hemoglobin and albumin crosses filtration barrier very poorly, because they are proteins. A very poor passage. But whatever it is, whatever little passage it has, the passage of hemoglobin is 3 times more than of the albumin. It is due to shape principle. So these are the three important determining factors of the solutes which are undergoing passage through the glomerular filtration barrier. So this is the filtration barrier. This is less than equal to 5,000, or effective molecular radius must be less than equal to 15 angstrom. Now, the substance which can easily pass through the glomerular filtration barrier, and thereby concentration of that substance in the filtrate and plasma are same. If a substance can easily pass through the glomerular filtration barrier, then the concentration of that substance in the plasma and filtrate will be same. So F by P ratio will be 1. So when F by P ratio is equal to 1, we call it freely filterable substance. Freely filterable substance means F by P ratio is equal to 1. So all the electrolytes like sodium, potassium, calcium, bicarbonate, Cl minus, etc., all are freely filterable substance. So then glucose, urea, uric acid, etc., all are freely filterable substance. So that is the definition of the freely filterable substance. Now let us try to understand the filtration problem. So these are some of, till now I somehow described some of the parameters. Now let us enter into the understanding of filtration phenomenon. Now, glomerular filtration, as the name suggests, it is basically a capillary filtration, and we all know substantially about the capillary filtration. We have learned in detail during our cardiovascular days. So this is a typical capillary. This is a typical capillary: arteriole, meta-arteriole, precapillary sphincter, then capillary, then venule, etc. Now, if we see a simplified diagram of a capillary, what I have shown you in my last class also. So this is the arteriolar side of the capillary. This is the venular side of the capillary. This is the arteriolar end of the capillary. This is the venular end of the capillary. And on it, so this is the arteriolar end, this is the venular end, and on it, plenty of forces. Some are moving outside, moving the fluid outside, some are moving the fluid inside. They are acting. Now, in order to understand the glomerular filtration, we need to understand the filtration in the ordinary capillary in a very clear-cut term. Very clear-cut term, we need to understand first that. So, we know there is a Starling's equation. This is J is equal to K, Pc minus Pi minus Pi C minus Pi I. Kf is the coefficient of filtration. Pc is the capillary hydrostatic pressure. Pi is the interstitial tissue hydrostatic pressure. Pi C is the capillary oncotic pressure. Pi I is the interstitial tissue oncotic pressure. And accordingly, you can calculate the rate of filtration. We ordinarily do it at the arteriolar end of the capillary and in the venular end of the capillary. We calculate both ends. That is the usual custom. We usually calculate both ends. Filtration is taking place throughout the capillary, but customarily we calculate them at the arteriolar end and venular end. Now, if we do that in any extrarenal capillary like this ordinary capillary, see the hydrostatic pressure is around 40 millimeter of mercury in the arterial end, or rather arteriolar end, and in the venular end it is around 10 millimeter of mercury. Pi is around 2 millimeter of mercury. Interstitial tissue hydrostatic pressure due to fluid present in the tissue space, that means the tissue fluid or interstitial fluid. Pi C means capillary osmotic pressure, it is around 25 millimeter of mercury. In the blood, Pi I, that means little amount of protein is also present in the tissue fluid. It causes oncotic pressure of the tissue fluid, that is around 3 millimeter of mercury. So all these forces are compiled in the arteriolar end and venular end, and if you compile them, you will find it is around plus 16 millimeter of mercury at the arterial end or arteriolar end, and minus 14 millimeter of mercury at the venular end. I have discussed everything, all these things during our cardiovascular days. Now, what does it imply? What does it imply? It implies that there is a net fluid shift from the arteriolar end of the capillary, from the vascular space to the extravascular space, from inside the vessel to the tissue space, and there is a net shift of fluid from the tissue space to the intravascular space in the venular end. In the arteriolar end, it is around the net filtering pressure is plus 16 millimeter of mercury. In the venular end, it is around minus 14 millimeter of mercury. So fluid is moving out of the arterial end of the capillary, and fluid is getting inside the capillary to the venous end. So this is the venular end. So these are the modus operandi, mode of operation of the capillary filtration in any ordinary capillary. That we understand. Now let us see what is happening in glomerular capillary. So glomerular capillary is a very peculiar capillary, what I have described in my last class. Here, the capillary is originated from an arteriole, but it is ending into an arteriole instead of a venule. So that is the speciality of the glomerular capillary. It is starting from an arteriole and end up in an arteriole. That is the very typical feature, and this is the feature of the glomerular capillary. Here, instead of arteriolar end and venular end, we call it afferent arteriolar end and efferent arteriolar end. So this is the afferent arteriolar end, this is the afferent arteriolar end, and this is the efferent arteriolar end, and this is the filtration barrier, and this is the so-called tissue space or Bowman's capsular space. Now, for its operation, so this is the filtration, and this filtration is known as glomerular filtration. Now, for its operation, we are comparing the two kinds of capillary. This slide I have also shown in the last class. So this is the ordinary capillary, arteriole and venule, afferent arteriole and efferent arteriole. So this is the remarkable difference between these two kinds of capillary. Now let us see the Starling's equation. So this is the Starling's equation, what I have already described. What I have already described, applicable or implicable in an ordinary capillary. Now for the glomerular capillary, it is a modified Starling's equation. We just modified it like this. So instead of PC, we call it PGC. That means hydrostatic pressure of the glomerular capillary. Instead of PI, we are calling it PBC. That means hydrostatic pressure of the Bowman's capsule. Accordingly, pi GC and pi BC. Right? So this is Kf is filtration coefficient, Pg is glomerular capillary hydrostatic pressure, PBC is Bowman's capsule hydrostatic pressure, PGC is capillary oncotic pressure, and PBC is Bowman's capsule oncotic pressure. Now, truly speaking, as proteins are not passing through the filtration barrier in the Bowman's capsule, there is hardly any protein is present in the Bowman's capsule. So Bowman's capsule oncotic pressure is virtually zero, virtually nil or virtually zero. We can ignore that. And accordingly, we can rewrite the Starling's equation, ignoring this pi BC as a J is equal to Kf PGC minus PBC minus pi BC. Simple. So that is the modified Starling's equation. Now let us see how it is operating. See, it is operating in the glomerular capillary hydrostatic pressure is a bit higher than ordinary hydrostatic pressure. Ordinary capillary hydrostatic pressure, it was 40 in ordinary capillary, it is 45 here. Now hydrostatic pressure of the Bowman's capsule is measured to be 10 millimeter of mercury. Now another interesting thing happens that pi GC means oncotic pressure of the glomerular capillary. In case of ordinary capillary, oncotic pressure remains same throughout the capillary. But in case of glomerular capillary, as large amount of fluid is shifted out of the vascular lumen, at the efferent arteriolar end, the blood becomes much more concentrated and the relative concentration of protein is increased, as a result of which at the efferent arteriolar end, the oncotic pressure increases. So in case of ordinary capillary, oncotic pressure remains same, 25 millimeter mercury. In case of glomerular capillary, it is 25 in the afferent arteriolar end, but the efferent arteriolar end, it is 35 because there is huge amount of fluid is transferred. I will show you very soon in a diagram. If you calculate that, at the afferent arteriolar end, the net filtration pressure is 10, and efferent arteriolar end, the net filtration pressure is 0. 45 minus 10 minus 35 is 0. So fluid is coming out near the afferent arteriolar end, but no fluid is returning in the efferent arteriolar end. So there is a net filtration. In case of ordinary capillary, fluid is filtered out of the arteriolar end of the capillary, and fluid is absorbed in the efferent end of the capillary. Whereas in case of glomerular capillary, from the afferent arteriolar end, fluid is going out, and the efferent arteriolar end, nothing is returning in. So there is net filtration. Now let me show you this operation by my very poor handmade drawing. but I think that will be more helpful for you. So I try to draw it. So this is the typical glomerulus or glomerular capillary, and in one side and on the side is the this is the Marvan's capsule. So 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 this is the afferent arterial end, afferent arterial end. This is the afferent arterial end, and this is the efferent arterial end. So this is the efferent arterial end. So this is the afferent arterial end, and this is the efferent arterial end, and this is the glomerular capillary plexus. Here the filtration is taking place. So this is the site of filtration. Site of filtration. Now let us see how filtration is happening. Now in the here, somewhere here, if we try to in the afferent arterial end, the PGC is around 45 millimeter of mercury. PGC is around 45 millimeter of mercury. Then pi GC, I cannot draw pi here. Pi GC is around 25 millimeter of mercury. Pi GC is around 25 millimeter of mercury, and PBC is around 10 millimeter of mercury. So if we do the modified Starling's calculation, so 45 minus 25 minus 10 is equal to 10 millimeter of mercury. So this is the net filtration pressure. This is the net filtration pressure here. We can write like that. This is the net filtration pressure here. That is the 10 millimeter of mercury. Or effective filtration pressure here is the 10 millimeter of mercury. Of mercury. Now, when the fluid or blood reaches here, let us see what will happen to the situation here. Here, the PGC will be same, 45 millimeter of mercury. This will be same. Why it is so? That is the reason. You see, in case of glomerular capillary is starting from an arteriole and end up in an arteriole. So there is no pressure drop. In case of ordinary capillary, there is a pressure drop in the venular end. In the venular end, there is a pressure drop in the venular end. But in case of glomerular capillary, there is no pressure drop in the venular end because both the end are arteriolar end. So PGC is maintained. And pi GC is increased from 25 to 35 millimeter of mercury. The reason I have told you, because there is lot of fluid is lost here, and there is a relative concentration of protein at the efferent arterial end. And PBC, as usual, is around 10 millimeter of mercury. And ultimately, the result is 0 millimeter of mercury. So we can very clearly see there is only fluid is moving out. Fluid is moving out, but no fluid is getting in. So fluid is moving out, but no fluid is getting in. No fluid is getting in. Only fluid is moving out, but no fluid is getting in. So this is the mechanism of filtration. So this is the mechanism of filtration utilizing this modified Starling equation and knowing the necessary differences between an ordinary capillary and a glomerular capillary, we can simply calculate out these two situations at the apparent arteriolar end and efferent arteriolar end. So, if I just repeat one issue, that is, I time and again told you in my last class also that glomerular capillary is a very special feature, that this capillary is starting from an arteriole, end up in an arteriole, and the implication is, as it is originating from an arteriole and end up in an arteriole, there is no drop in pressure. Pressure maintains. Whereas in ordinary capillary is starting from an arteriole but end up in a venule. That's why there's a drop in pressure. And as the pressure is not dropped in glomerular capillary, accordingly, the filtration becomes possible. So this is a kind of a manual representation of my presentation by my poor handmade drawing. So this is the mechanism of filtration. And if I repeat again, so this is, you can see like that, it is 45 millimeter of mercury, and efferent end is 45 millimeter of mercury. PBC is same, but pi GC increased from 25 to 35. As a result, there is net filtration pressure. At the apparent arterial end is 10, and the efferent arterial end is 0. So this, and that's why the filtration becomes possible. Next issue is the measurement of GFR. How to measure the GFR? What is the principle of measurement of GFR? Principle of measurement is our age-old Nephron equation. In the first class, I described in detail about this Nephron equation. What is UXV? It is a filtered load. What is PXGFR? It is the filtered load. What is TX? It is the transport. If it is plus, it is secretion. If it is minus, it is reabsorption, and is ultimately the urinary load. Urinary load. So it is dealing with a substance X. Its urinary load is dependent upon the filtered load plus minus transport. If the transport Tx is equal to PXGFR, then the urinary load will become 0. If the Tx is equal to and opposite to PXGFR, if the Tx is negative and it is equal to PXGFR, then UXV will be 0, as we see in case of glucose, right? Or if the Tx is positive, then there is substantial UXV, substantial urinary load. Now, based upon this Nephron equation, we measure the GFR. How? I will show you. I will choose a substance whose Tx is 0. I will choose a substance whose Tx is 0. If the Tx is 0, then GFR is equal to UXV by Px. If the Tx is 0, then GFR is equal to UXV by Px. Point is, what is that substance whose Tx is 0? Or what is the meaning of the phrase or the statement that Tx is 0? What is the meaning of this? What is the implication of this? When we say Tx is 0, that means it is a substance which is neither reabsorbed nor secreted. Which is neither reabsorbed nor secreted, which is only filtered. Which is only freely filtered, but it is neither reabsorbed nor secreted. It remains completely unprocessed during its tubular passage. If we find such a substance, and inject that substance to the person and measure these respective values, Ux, Px, V, etc., and by knowing the concentrations of that substance in plasma, of that substance in urine, we can measure out the GFR. Point is, what is such substance whose TX is 0? That means who is neither reabsorbed nor secreted. That such substance is known as inulin. We have got a substance which is a fructose polymer having a molecular weight of around 5,000, which is freely filtered, which is not reabsorbed, which is not secreted, which is not metabolized. If it is get metabolized, then it will be give us the erroneous result. So inulin is such a substance, it is a fructose polymer, which is freely filtered, not reabsorbed, not secreted, and not metabolized. So if we use such a substance and inject the person with that substance, and after some time, after achieving the steady level, if we measure the urinary concentration of inulin, plasma concentration of inulin, and rate of urine formation per unit time, we can simply calculate out the GFR, and in that way, the GFR is calculated. So, using inulin, we can calculate GFR. So, there are certain other implications of this GFR estimation, which I am not presently telling. If I find time, we shall tell that when we shall discuss the clearance issue in later classes. Then I will cover those issues. Now we know the nephron functions, and this is the PXGFR, that is filtered load. This is the urinary load, and this is the TX. Now, how the GFR is regulated? GFR is regulated by several factors. Like regulation in the cardiovascular system, GFR is also regulated like that. That autoregulation or local autoregulation, neural regulation, and hormonal regulation. Apart from that, there is another very important issue of afferent arteriole-efferent arteriole resistance ratio. The issue item which I have introduced in my last lecture. So, what is afferent-efferent resistance ratio? See, so this is a glomerulus, this is glomerulus, this is glomerulus, this is afferent arteriole, and this is efferent arteriole. And as both are arteriole having a strong circular muscle coat, or rather single unit circular muscle coat, which are highly stretch sensitive and thereby showing vasoconstriction, the relative resistance of this afferent and efferent arteriole largely influencing the glomerular function. Let us see one by one. Suppose this is a situation where there is afferent arteriolar vasoconstriction with normal efferent arteriole, or without any constriction of the efferent arteriole. What will happen? As there is afferent arteriolar constriction, the hydrostatic pressure of the glomerular capillary will reduce, and GFR will be reduced, and renal blood flow will also be reduced. It is quite rational. We can very well understand. I am just giving you certain illustration, certain situation where afferent-efferent resistance ratio is influencing the glomerular function. So this is the certain situation where change in afferent-efferent resistance ratio will alter the glomerular function. So if afferent-efferent resistance ratio is increased very high, then the PGC will fall, GFR will fall, and renal blood flow will also fall. In the next issue, where the afferent arteriole is otherwise regular, but there is efferent arteriolar vasoconstriction, so afferent-efferent resistance ratio is reduced. If that is so, then PGC will increase and GFR will increase, but renal blood flow will remain compromised. As there is more, as there is a very end point constriction, but blood is coming as such, the hydrostatic pressure of the glomerular capillary will rise, leading to increase in GFR. Another thing is, if there is constriction of the afferent arteriole and dilatation of the efferent arteriole, constriction of the afferent arteriole and dilatation of the efferent arteriole, what will happen? Almost the second one, that means PGC will definitely fall, GFR will fall, but as there is huge dilatation, renal blood flow or distal renal blood flow will increase to some extent. And in another situation, if there is afferent arteriolar vasodilatation, but efferent arteriolar vasoconstriction, afferent arteriolar vasodilatation, but efferent arteriolar vasoconstriction, what will happen? The hydrostatic pressure of the glomerular capillary will rise. Similarly, the GFR will rise, but RBF will also rise, because although there is peripheral constriction, but as there is afferent arterial dilatation, large amount of flow will be there, and large flow will offset this resistance and will increase the flow. So there are plenty of such situations. There are variable permutations and combinations of different value of afferent-efferent resistance ratio, and they will appropriately and respectively influence the glomerular function or the extent or rate of glomerular filtration or GFR. Now this glomerulus, if we see, this is a picture of a juxtamedullary nephron. See, both the afferent arteriole and efferent arteriole are quite almost similar in nature, almost of same diameter in nature. Whereas if we see in case of cortical nephron, the afferent arteriole diameter is more than the efferent arteriolar diameter. There is substantial efferent arteriolar, substantially low efferent arteriolar diameter. Accordingly, as per our principle of afferent-efferent resistance ratio, the functioning of cortical nephron will be appropriately modified or influenced. You can calculate it out. That may be a home task. You can think that what will happen to the altered glomerular function between the juxtamedullary nephron or long loop nephron and short loop nephron or cortical nephron. Next point of regulation is autoregulation. During our cardiovascular case, I took plenty of time, substantial time, to discuss autoregulation and mechanism of autoregulation. I think it is enough to show you this diagram only. So this is the renal blood flow. That means that within a range of physiological range, even with increase in the perfusion pressure, the flow per unit time will not change. To a particular organ will not change. Even with increase in the perfusion pressure, flow per unit time in an organ will not change, and that is the definition of autoregulation. And that autoregulatory phenomena is clearly visible in kidney also. I am not going in detail about the autoregulation because I have tested this thing in substantial detail in cardiovascular system. And there are two broad mechanisms of autoregulation. One is myogenic theory, another is metabolic theory. I am just naming them. Myogenic theory and metabolic theory of autoregulation. Both are applicable here. If you forget it, just have a rehearsal, have a recapitulation. I don't have much time to discuss it further. So mechanism of autoregulation is myogenic theory and metabolic theory. Myogenic mechanism or metabolic mechanism of autoregulation. If you forget it, please recapitulate. Then lastly, the almost penultimate is the neural regulation. As usual, like cardiovascular regulation from the sympathetic. So it is mainly sympathetic innervation. Sympathetic innervation. Vessel walls are rich sympathetic twig. So this is a sympathetic chain from which sympathetic twig are reaching the vessels and have a rich sympathetic innervation in the renal vessels. So in case of sympathetic activity, there will be profound renal vasoconstriction. In case of sympathetic activity. And that is the reason why during exercise, kidneys are getting very minimum amount of blood. There is overwhelming renal vasoconstriction. I have told it. during my cardiovascular test, during the discussion of exercise. So during exercise, when there is increased sympathetic output or sympathetic activity, there will be profound renal vasoconstriction and renal blood flow is severely reduced or severely compromised. So this is about the neural regulation. And finally, the hormonal regulation. Hormonal regulation. As usual, these are circulatory vasoconstrictors and circulatory vasodilators. So circulatory vasoconstrictors are as usual epinephrine, norepinephrine, angiotensin 2, arginine, vasopressin, endothelin, etc. Or vasodilators are bradykinin, nitric oxide, etc. So these are circulatory vasoconstrictors and vasodilators, or in one word, circulatory vasoactive substance. As usual, like all the systemic vessels, they are also acting on the renal vessels and causing respective vasoconstriction and vasodilatation. Lastly, I will take up another issue, another important issue in connection with this glomerular apparatus is the juxtagmerular apparatus. What is juxtagmerular apparatus? Try to understand it very carefully. I will recapitulate the picture of nephron. If you examine this figure carefully, you will see that this is glomerulus, continuing as Bowman's capsule, continuing as proximal tubule, then loop of Henle, returning as distal tubule, and this distal tubule is coming in very close contact with the parent glomerulus, parent Malpighian corpuscle, from where it has originated. The very distal nephron or distal tubule is coming in very close contact, very close association with the glomerulus, and it is passing in between the afferent and efferent arteriole of that particular glomerulus. You understand? So this is the region. This is the region where the distal convoluted tubule is coming in very close contact with the afferent and efferent arteriole of the very nephron from where it is originated. So this is a very curious feature. It is as if filtrate which is formed here and that filtrate when undergo processing throughout its passage in the tubule, and this processed filtrate or semi-processed filtrate are coming in close contact with that region where filtrate is produced. This semi-processed filtrate are coming in contact with that region where the original filtrate was originally produced. If we see it more carefully, so this is a top view of the JG apparatus or juxtagmerular apparatus. If we see from the top, this is the afferent arteriole, this is the glomerular capillary plexus, these are the Bowman's capsule, and this is continuing as proximal tubule, and that proximal tubule traversed ultimately to the loop of Henle and finally ascending up, and when it is ascending up, it is ascending in between the afferent and efferent arteriole. Ascending in between the afferent and efferent arteriole and coming in very close contact with especially the afferent arteriole. And here you see these distal tubule is coming in very close contact with the afferent arteriole, and see there is certain amount of cellular modification. Both the cells here, if you clearly examine the cells, see the cells present here has got multiple dense nuclei. See, small but multiple dense nuclei, and this multiple dense nuclei is known as macula densa. And here in the endothelial wall, there is also change in the structure of the endothelial wall. It becomes granular in nature. There are plenty of granules present here. Granule means they are basically the vesicles, cytoplasmic vesicles. So these cells are known as granular cells because they are apparently look like granules. These cells are known as macula densa, and whole thing is known as JG apparatus. This whole thing is known as JG apparatus. If we imagine an equilateral a triangle whose two limbs are afferent and efferent arteriole, and base is this, base is the distal tubule. So this is constituting the JG apparatus. If we see more carefully, see, this is afferent arteriole, this is efferent arteriole, and the base is formed by this distal tubule, that is macula densa, etc. And in between, this is a triangular space. In the triangular space, there are certain loose cells are seen. Loose cells are seen. These are known as lattice cells. These are known as lattice cells. As a whole, this is known as JG apparatus or Juxtagmerular Apparatus. So this JG, if it is asked to you what is JG apparatus, you must describe the JG apparatus as I have just did that description. And the composition is a macula densa, which is a portion of distal tubule or modified distal tubule, granular cells, that is the modified afferent arteriolar cells, and finally the lattice cells, which is remaining in the triangular space. These lattice cells are nothing but extra glomerular mesangial cells. Extra glomerular mesangial cells. What is mesangial cells? I have described during my cardiovascular test. Please recapitulate. I don't have time to discuss it further. I discussed during my cardiovascular test. These lattice cells are extra glomerular mesangial cells. These mesangial cells are loose pericytes, mesangial cells, extra glomerular mesangial cells. So this. Now, what is the function of juxtagmerular apparatus or JG apparatus? That is quite curious. I have told you this is a zone of interaction between the area of genesis of filtration and area of semi-processed filtration. Filtration is produced in the glomerulus, and filtration after a substantial processing in the distal tubule, it is coming in close contact with that area where it has originally produced. So there are certain feedback loops here. If there is some alteration or there is a change in the filtrate processing, there are some feedback loops which can modify that filtrate creation at the origin level. I will discuss all these things in subsequent classes. This specialized function of JG apparatus. So finally, I enlisted during my first class the functions of nephron. I told you nephron has got two broad category of functions. One is filtration, another is transport. If transport of the molecule is towards the tubular lumen, it is called secretion. If the transport of molecule is away from the tubular lumen, it is called reabsorption. So these are the two function or three function, that means glomerular filtration, tubular reabsorption, and tubular secretion. So three functions accordingly I have to discuss with you, and today I somehow finish the filtration. So discussion of filtration I somehow covered. If you have any question, for this, please ask the question. Inculcate an habit of asking question. Send me the question or post it in the group. I am here to answer each and every question of you. Thank you.